All right, welcome back today. So I think today we're talking about MCD spectroscopy kind of as an add-on to your magnetic day yesterday. And let me ask you, because that's not a very widespread technique, like who has like ever measured an MCD spectrum or has been involved in an MCD study then? Okay, yeah, well, you guys don't count. Here's what, so few of them. All right, so MCD is a really super cool technique, and I hope that I can sell to you what makes it so cool. And let's start by talking about where it comes from. All right, me and that pointer, that is... that's no, it's okay. I think I can do it. Yay! All right, so MCD started with the discovery of the Faraday effect. And so Michael Faraday, like one of the great pioneers, he observed the following. So we don't need to go through all of this. That is an entry from his diary. Essentially what he observed is the following. It's not the MCD effect, but a linear dichroism effect. So what he did is he took a sample and placed a horseshoe magnet over it and then measured how much linearly polarized light gets tilted by passing through the sample as a function of magnetic field. Yeah, and that magnetic this magnetic tilt, that is the effect that he had, and that is given the name Faraday effect. And he figured that it's linear in the magnetic field, and he gave a very simple equation that the rotation of the plane polarized light by that angle is proportional to the path length, the strength of the magnetic field, and then something molecular that he called the Verde constant. And so that is an actual picture of the magnet that he used. So that is Faraday's actual horseshoe magnet that is still in the Faraday Museum in London. So here you see that experiment. You have the linearly polarized light, and the electric vector is like swinging perpendicular to the propagation direction. And then after it passes through the sample, then that electric vector is being rotated. Yeah? And today we're doing a slightly different experiment that is, however, closely related. So it's related by a mathematical transformation, and that is the magnetic circular dichroism experiment. And the way it works is the following. So instead of using linearly polarized light, you use circularly polarized light. And at first glance, it is simply the same as a standard CD experiment, just in the presence of a magnetic field. And by and large, that is what it is. However, it is a way more elaborate experiment for experimental reasons that I will go into in a moment. So you start here by having a light source, and that light source that is emitting light, a spectrum of light, and it passes through a monochromator, and then what is called a photoelastic modulator. And the photoelastic modulator that is using the piezoelectric effect in order to produce right or left circularly polarized light. It's basically squeezing a crystal with a certain frequency. Yeah, and so it's not, the way it's being done, it's not that it's producing either right or left circularly polarized light, but it is alternatingly producing right and left circular polarized light with a certain frequency that is, say, 100 kilohertz or so, right? And so it's basically these like pulses of RCP and LCP photons are hitting the sample. The sample is sitting here in a magnetocryostat, so that's a pretty massive thing that you have certainly also seen in the lab. And then after it passes through the sample, it's being detected. And that detection now needs to be phase sensitive, right? So you know that you modulate between RCP and LCP with, say, 100 kilohertz frequency. That means your detector must like listen with the same frequency of, like, say, 100 kilohertz, like RCP, LCP, RCP, LCP, RCP, LCP, etc. And what you can deduce then from that is the MCD signal that is defined as the difference in absorption between left circularly polarized photons minus right circularly polarized photons minus the signal at zero magnetic field. So the signal at zero magnetic field, that is a natural CD. Yeah? And the natural CD, as you know, requires substances that don't have a center of inversion, like symmetry-wise. And the same restriction does not hold for MCD. So MCD exists in all matter. So every molecule on this planet has a non-zero MCD spectrum, whereas many have a zero CD spectrum. Yeah? But the CD is our baseline. And now you can write a very innocent-looking equation, and we will start developing the information content of that experiment further. So you can measure then this differential absorption of left and right circularly polarized light as a function of the wavelengths that you apply, as a function of the magnetic field, and as a function of the temperature. Yeah, so you have three experimental variables that you can vary, and that's why it's a three-dimensional experiment, if you want so. Yeah. Okay. Yeah, and so if you write an innocent-looking equation in terms of quantum mechanics, you can write that this differential absorption is proportional to the concentration of the sample, the path length, the energy difference, and then you have a bunch of initial states. So these are the states that are thermally populated at the temperature that you have applied. So these are all of these initial states J here. And Nj, that is the Boltzmann population of that state, right? And so any state with a non-zero Boltzmann population in the ground state multiplet, so typically the magnetic sublevels of that ground state, will contribute to the MCD spectrum, and then you reach a bunch of final states, and then it's simply what is this here is simply the difference in the probabilities of absorbing an LCP photon minus the probability of absorbing a RCP photon according to Fermi's golden rule. So if I, oh yeah, and I wanted to say these magnetocrystals, they're pretty elaborate things. You can vary the temperature typically between, say, 1.5 Kelvin and at least liquid nitrogen. You can also measure MCD at room temperature, and many of the companies that sell CD spectrometers also have an MCD add-on, and that MCD add-on, that is an absolutely horrifically overpriced magnet that you simply place into the CD compartment, in the sample compartment, and nothing is a problem. If you really go to town with it and go to liquid helium temperatures and very strong magnetic fields, so that can go to 10 or 11 Tesla, these magnets, then the experimental apparatus looks way more elaborate. So I've already shown you that picture, but in order to drive home what's happening physically, yeah? So we have the electronic ground state multiplet, and that has all of the magnetic sublevels of the ground state, and if it's non-degenerate, these are the 2s plus 1 components of a ground state with a total spin of s. And then you have all of these electronically excited states that you also probe in absorption spectroscopy, and they have a spin s prime, and that means they have 2s prime plus 1 components, and they're all there. Yeah. And now once you start turning on a magnetic field, then these magnetic sublevels will start to diverge, and these splittings here, they are probed then by EPR spectroscopy and endor spectroscopy and everything. The transition between the electronic states, that is like many orders of magnitude higher in photon energy, that is probed by absorption spectroscopy. But now, of course, once you start splitting these levels here, then you're getting new effects. And so it's kind of a combination of, you can think of the MCD as bridging between absorption spectroscopy, EPR spectroscopy, and in particularly magnetic susceptibility. So what you have heard from Dan yesterday, and it is not very wrong to think that you can use the MCD in a way that is a kind of optical measurement of the magnetic susceptibility. It has key advantages over measuring the squid, but it's a more elaborate experiment also than the squid. Yeah, so that is the prime virtue of MCD spectroscopy, that it kind of combines, like brings the worlds of magnetic spectroscopy and optical spectroscopy together, and that is what makes it also so powerful and so much fun to work with, that once you start analyzing the absorption spectrum and start analyzing the EPR spectrum, the MCD sits right there in the middle, and you can somehow find again what you've measured in the EPR, you will also find and need in the MCD, and what you've measured in the absorption, you'll also find in the MCD. And altogether, it is a really great data set to get a coherent, experimentally substantiated picture of the electronic structure of the compound. So, as I said, it's a three-dimensional experiment, and there has been an early theory for that, and the early theory for that was done by Phil Stevens, and he has identified three principal mechanisms for the MCD, and these are the famous MCD A, B, and C terms. Yeah, and so this is a generic equation of how these A, B, and C terms work. And so delta epsilon over E, that is essentially proportional to the difference in absorption. And according to Stevens' theory, that is linear in the magnetic field. Gamma is a random, no, not random, but it's a collection of natural constants. And beta is the Bohr magneton. And so the characteristic feature of the A term is that it's a derivative-shaped signal. Yeah, so f of E is a line-shaped function, for example, a Gaussian, and that means the derivative of f with respect to E, that is a derivative-shaped object. Then the B term and the C term, they're absorption-shaped, but they can be positive or negative. And what differentiates the B and the C term is that the C term is temperature-dependent. Yeah? So the A term is not temperature-dependent, but gives you a derivative-shaped signal. B gives you an absorption-shaped signal, but temperature-independent, and C gives you a temperature-dependent absorption-shaped signal. And we will look into the physical origin of these in a moment. Yeah? But now you can do more. So let's say you've measured an MCD spectrum like this one here, and it has some positive peaks and some negative peaks. Some look very derivative-shaped and some look absorption-shaped. But what you can do is now to set the spectrometer to a fixed frequency, or in this case a fixed wavelength, and start varying the magnetic field and the temperature. And what you will get then is these isotherms, or these magnetization curves. So what you're plotting here is the MCD signal as a function of the dimensionless variable beta b divided by 2kt. And so you've seen very similar curves in your lecture on squid and magnetism, and this is very similar. And so what you can deduce then, it has been in closed form proven that the MCD signal for an S equals 1/2 system varies as a constant times the hyperbolic tangent of g beta b divided by 2kt, and you will see that all of these are natural constants except the g value, and that means you can in principle measure the average g value of the sample by MCD spectroscopy. In very favorable cases, you also get a low resolution picture of the anisotropy in the G tensor, but if you can measure the EPR spectrum, that's a much more accurate measurement of the G tensor than is the MCD. However, the buck doesn't stop there. It gets way more interesting when the total spin is larger than 1/2, and I'm going to talk to you about that later. So here are some pictures of how that looks in practice, and I know you have seen the lab, so I can keep that short. So there's a whole lot of electronics here. Then there is the CD spectrometer, there is a magnetocryostat, and down here is the detector. These are all standard components, but you have to separate them spatially, and the reason is that these magnets, they're creating stray fields, and these stray fields are not that small. And so these stray fields are interfering in a negative way with the photoelastic modulator that is creating the circular polarized light, and it's also interfering with the detector. And so if you don't isolate them, so you see the detector here is shielded by mu metal. If you don't isolate the detector and put some distance between the magnet and the modulator, all you're measuring is artifacts. And it still looks like a relatively simple experiment, but it really is not. So I've known quite a number of groups who have bought the equipment to build an MCD spectrometer and never got it running. So the first time we built an MCD spectrometer here, it took us 2 years before anything useful came out. And then we wanted to build a second MCD spectrometer that covers the full range from 2000 nanometers to 200 nanometers, and say, yeah, now we know how it goes. And the way it went, it took us another 2 years to make that work again. So in case you are interested in building an MCD apparatus, and there are no commercial full range MCD spectrometers, then be careful, and my very, very strong recommendation is hire a physicist. You will need a physicist to make this work. Okay, so now of course we have the situation that we're potentially at liquid helium temperatures. And so what happens if you take your aqueous solution and you freeze it down to liquid helium temperatures, is it becomes ice, right? And that ice is full of cracks and is opaque. But at the end of the day, of course, we need to get some photons through the sample so that we can measure something on the other end. Yeah, and that is the principal experimental difficulty here. You have to have a glass. Yeah, and so that means you have to use a solvent or a solvent mixture that, when you freeze it, gives a glass. And that is quite an art form. So there are tables full of recommendations of solvents that you can use, like mixtures of methanol and ethanol, or if you're working in aqueous solution, then you can add 50% of glycerol or so. And then with a bit of skill and a good steady hand, you will normally be able to freeze a sample into a glass. Then all kinds of things can still go wrong, but by and large, the first thing is that you have to have glass. And so the sample sits here in one of these sample cells, and that is, they're made out of copper metal because they need to be thermally conductive, right? So you want that the temperature at the sample is actually the temperature that you put into the cryostat and not 5 degrees higher, so that needs to be thermally conducting. And so the first step when you do an MCD experiment yourself is to take such a cell, and there are two quartz glass windows that you put in here. Then you put such a rubber spacer, then you put another window, then you put that thing on top, then you screw everything together, and now you have to fill it. And in order to fill it, you need about 3 hands. And most of us only have 2. But so because you need 1 needle to stick it into syringe your sample in, and then you need 1 hand to take the exit syringe, because like the gas that was in the sample chamber before needs to exit somehow. And the 3rd hand needs to hold the sample holder. Yeah? With a bit of contemplation, you can do it. It starts to become real fun when you have to do that in a glove box. That is quite difficult, but it's doable. And so what you do then is you screw that sample like onto a rod, and that rod is inserted from above and oriented such that hopefully the light can pass through. And if you have a nice glass, it is also not collapsing when you cool down to liquid helium temperatures, then you can measure your MCD signals. All right, let's give you like a really coarse overview of the kinds of things that you can do and why MCD is cool. And the first thing that you see is cool here. So how many of you have measured an absorption spectrum like all the way out to 2000 nanometers? Yeah. And how many of you know what happens if there are even traces of water in the sample? Yeah, you get like vibrational overtones from water vibrations that have a huge peak here at around 1400 or 1500 nanometers. And that makes it very difficult to measure the absorption in the near infrared region of the spectrum. But MCD doesn't have such a problem. It's a differential measurement. And that's why it's no problem, unless there is so much water in the sample that you can't get any light through anymore. And in this case, you have to use diode like D2O. But MCD being a differential measurement of left minus circular polarized light is not sensitive to that, and that's why it's a great technique to measure in the near infrared region of the spectrum. And many of the important D2D transitions in transition metal complexes actually happen in the near infrared, and that's why it's a great way to measure to measure these excited states. Then trivially, like the CD, the MCD is a signed quantity, and that means it offers way more resolution than just the absorption spectrum. For example, here that's an absorption spectrum of a medium-sized molecule, and it's pretty broad and like not particularly featured. But if you look at the absorption, the CD and the MCD together, there is a lot of bands that you can resolve. And that's why it's great if you are really serious about comparing theory and experiment, and you want to suck the maximum information content out of the experiment, then it's a great idea to measure all of these three spectra together and then do simultaneous Gaussian resolution, as I said before. Now, MCD is kind of a bit difficult, and so before we even start to address the question, so when is that peak negative and when is it positive, people have used it just to fingerprint. And that is just simply by making a library of spectra and comparing. And so, for example, these are spectra of different iron porphyrins, and as you know, the iron porphyrins, they can be high spin iron 2, low spin iron 2, high spin iron 3, or low spin iron 3, can also sometimes be intermediate spin. And it turns out that they have very, very, very characteristic and different MCD spectra. And just imagine you have, you're a biochemist and you isolate a new enzyme and you know there's porphyrin in it and you want to know what's the oxidation state of the metal. You measure an MCD spectrum and you can find it out. It also turns out, for the case of low spin iron 3 iron porphyrins, that the MCD in the near infrared region is very sensitive to the axial ligand that is coordinating to the iron. And so what people have done, these were a pioneering group in Norwich in the UK, they have measured known iron porphyrins in the near IR, and they were able to make such a table. And like, I'm very sorry, it's very poor quality then is, but basically on the basis of such a table, you can get a very good idea what the axial ligand to the iron is, or whether it's there in the first place or has dissociated, say, in the course of the reaction. And that is a good use of MCD. And that has nothing to do with any quantum mechanics, no calculations involved, no complicated analysis involved, nothing, just measure and fingerprint. And it's absolutely not wrong to do that, right? I mean, you can use, you can get a fair fraction of the total information content of these spectra by just fingerprinting, and many people use it this way. Now here's then a great asset of something that you can do with MCD that is really quite hard to do with any other techniques, and that is if you have mixtures. For example, I mean, that maybe if you're a synthetic chemist, you have synthesized a compound, but there are impurities in it. But more commonly, if you're a biochemist and your enzyme or protein has more than one metal center or more than one chromophore. So what you would get if you measure the magnetism of such samples is you always get the grand total of everything, right? That's what you measure in the squid. But in the MCD, all that you need is a region of the spectrum where only one of those chromophores absorbs. So for example, here is the case of cytochrome C oxidase that has a copper A center, has a heme A, and then it has an active site that is a heme copper conglomerate, so it's quite complicated. But you can figure out that there is some absorption bands here, for example, where only the copper A site absorbs, whereas here is completely dominated by the porphyrin. So if you want to measure the magnetic properties, or you want to have a selective probe into one of the metal sites, all you have to do is to set your spectrometer to this wavelength or to that wavelength and then measure the magnetism of it. And that is great, because you will not be able to do this with a squid, right? So the squid is like really tragically sensitive to any kind of impurity or mixture, and it's very hard to disentangle. Yeah, whereas the MCD as an optical measure of magnetic susceptibility doesn't have these problems. So now we're coming to more of a fun part of it. So here is the case of a high spin transition metal complex. It's iron EDTA peroxide. That's a spin 5/2 system, and it has a very nice and interesting absorption spectrum here, and a nice interesting MCD spectra that has quite a number of well-resolved bands. And now you can measure the MCD signal as a function of magnetic field and temperature at any of these wavelengths here, right? That is called the variable temperature variable field, or VTVH MCD. And now, funny enough, you see that the magnetic response of the system is completely different whether you measure here, or here at 22,000 wave numbers there, or at 18,000 wave numbers here, right? So you get drastically different magnetization curves. So first of all, these are very nested curves, right? So as a function of beta b over 2kt, whereas these all overlay. And what's the origin of that? And the origin of that, in a nutshell, is that you can use the MCD to determine the polarization of the electronic transition, despite the fact that you're not measuring on a crystal, but on a selection of randomly oriented molecules. Yeah, so that is essentially what you're seeing here, is that the polarization of these transitions, they act as a kind of filter on the magnetism that you are observing. And that means you can get very intimate information on the nature of the excited states by fully interpreting that VTVH MCD. What you also get out, of course, is spin Hamiltonian parameters out of these fits. Yeah? So you can measure this, and what you will be able to deduce is, for example, the zero field splitting parameter. Yeah? So that's a lot of information. Yeah? And once you start interpreting the spectra in terms of the electronic transitions, and you know their polarizations, the expected polarizations, you have an experimental means of determining these polarizations. Very cool. Next feature is, as you have certainly heard in your EPR lecture, integer spin systems are problematic for EPR spectroscopy. Yeah? We have already seen that in Kramer systems, so like half integer spin systems, the relativity or zero field splitting will not be able to lift the full degeneracy, and it splits everything into Kramer's doublets, and then these Kramer's doublets behave effectively as effective spin 1/2 systems in the EPR. That's no longer the case when you have an integer spin system, so a non-Kramer system, because then the zero field splitting can lift the degeneracy completely, and if it's large enough, it may kill any EPR transition. Let's, for example, look here at a triplet state where the m sub s equals 0 component is lowest, so that would be a positive zero field splitting, and let that d be much larger than the microwave frequency. Yeah? Then you will have in the EPR, like all of the population here in the lowest state, and let that be the length of this arrow represent the energy of the microwave photon, and you can see you're not able to reach any of these levels. And that means these integer spin systems often have very ugly or even non-existent EPR spectra, right? So the absence of an EPR spectrum does not mean that your compound is diamagnetic, right? In integer spin systems, there may not be an EPR. But for MCD, that's not a problem. It couldn't care less, because what you're seeing are here these optical transitions, and whatever integer spin system and non-integer spin systems is all the same. And large zero field splitting or small zero field splitting also doesn't matter then. Yeah? So none of that is in any shape or form problematic. Now, of course, all of this is MCD spectroscopy in the visible region, but it becomes even I don't know if it's more interesting or less interesting, but you can also do that in the X-ray region of the spectrum, and that is so-called X-ray MCD or XMCD. So in physics, that's a very, very well-known experiment that is also very widely used in heterogeneous catalysis and similar. And so you see that that creates very, very, very rich spectra that you can then also interpret with the help of quantum mechanics. There is a certain culture in physics that I'm not going there. But I will only like launch a little warning, and that's saying that the words of chemistry and physics are upside down, right? So chemistry is LCP minus RCP, physics is RCP minus LCP. So either convention is fine if you're familiar with it. It's just when you switch from one word to the other, you have to multiply your brain by -1, which is okay. That is right. And so that is it. But that is let me give you a little bit of an example of how nicely you can use it. So as I said, MCD is a great technique in order to measure DD transitions in the near-infrared region. And one of those systems where that's really, really useful is high-spin iron II complexes. So high-spin iron II complexes, they're integer spin, so they have an S equals 2 ground state, and they're almost not accessible in the EPR, and then they're often pretty much colorless, so there are no prominent transitions in the visible region of the spectrum, and so it's not easy to get a good spectroscopic handle of them. Obviously Mössbauer is one, but the other is MCD. And now if you go through different coordination geometries from octahedral to square pyramidal to trigonal pyramidal to distorted tetrahedral, of course, ligand field theory tells you that the DD transitions, the ligand field transitions, they change in a very characteristic way that is reflecting the coordination geometry. And with MCD spectroscopy, you can nicely see that. So for octahedral complex, what you typically see are two transitions at around 10,000 wave numbers split by about 2,000 wave numbers. And so that is simply the ground state in an octahedral iron II complex. That's quintet T2G, so that's a triply degenerate ground state, is subject to a Jahn-Teller effect, and there is in principle one transition to a quintet E state that is doubly degenerate. That's also subject to a Jahn-Teller effect, but a much larger Jahn-Teller effect than in the ground state. Yeah, and so that is what you're seeing. It's either low symmetry splitting or Jahn-Teller splitting, but this is basically that quintet T2G to quintet EG transition here, or like in a one electron picture, the T2G to EG transition, and that is what you observe here. Now you take one ligand away, and that is obviously stabilizing the DZ squared orbital very much, and so these transitions then occur not at 10,000 wave numbers plus minus 1,000, but they occur at around 10,000 and 5,000 wave numbers. And so the occurrence of that low energy band here, that is then in conjunction with a 10,000 wave number band, that is then indicative of a square pyramidal side. Trigonal bipyramidal side has a totally different d orbital splitting pattern. There's two sets of E states, and then the DZ squared orbital is highest in energy, CA1 here. And that typically gives rise to one transition at around 7,000 wave numbers and one that is undetectably low beyond 5,000 wave numbers. So 5,000 wave numbers or 2,000 nanometers, that is for practical purposes pretty much the limit of where you can go. I'm not aware of an MCD or absorption spectrometer that can go below that, and below that then is a different domain of spectroscopy that is currently being explored. Yeah, and then for tetrahedral sites, they have roughly half the ligand field splitting of an octahedral site, and so instead of 10,000 wave numbers transitions, you get a pair of transitions at about 5,000 wave numbers, and that is then the signature of a tetrahedral site. So that's a great way of like using MCD to get some insight into the effective coordination geometry of transition metal complexes, and I hope that I managed to get to the point where I show you an example to an actual enzyme system. But before we do that, I wanted to dig a little bit into the theory of the MCD and try to demystify that a little bit. So I have already talked about the A, B, and C terms, and now we can go through very, very simple model systems in order to try to understand where these are coming from. And let's start with the A term. So the A term is arising in the simplest possible form when you go from a non-degenerate ground state to an excited state that is degenerate. Yeah, so for example, here we have a fictitious atom that where you start in a singlet S state that is non-degenerate, and you go to a singlet P state that is triply degenerate. So then in a magnetic field, the three components of the singlet P state will split into P minus 1, P0, and P plus 1. Yeah? And now there are selection rules, of course, on the allowed transitions, right? And because there is the conservation of angular momentum, meaning that the angular momentum of the universe always needs to stay conserved, and that means if you annihilate an RCP photon, you must compensate for that in the opposite way by transferring that angular momentum to the absorbing system. Yeah? And so it happens that the RCP transition is allowed to the P minus 1 state, and the LCP is allowed to the P plus 1 state. And as you can see, that means they occur at slightly different energies. Yeah? And since we're measuring LCP minus RCP, the result, if you now subtract the blue curve from the red curve, is then a derivative shaped signal. Right? So as we said, then the A term is a derivative shaped signal, and that is the mechanism how it comes about. By going from a non-degenerate ground state into a degenerate excited state. So A terms are relatively rare. In practice, you meet them in compounds like porphyrins that have doubly degenerate excited states, like E states. Now, the second, for the moment, I'm skipping the B term and I'm going straight to the C term. And the C term is the opposite. So now we have a model atom that has a singlet P ground state and a singlet S excited state. Yeah? And now the situation occurs. Now, of course, you have the same selection rules as for the A term, but you have the Boltzmann population. So I've shown you on the beginning that you have to sum over all of the possible initial states, and the possible initial states are all three of those. And they will have a Boltzmann population, right? And the lowest of these states will have a higher population than the highest in these magnetic sublevels, and that also means that it will have that here the RCP transition will have a higher intensity because that's directly proportional to the Boltzmann population. All right, and that means because of that population difference, once you subtract then the red and the blue, you get an absorption-shaped signal. Yeah, and that is reflecting the population difference. Now, of course, you know that the splitting here is diverging linearly with magnetic field, and that means that the intensity of that signal is not only proportional to the magnetic field, but also to the temperature, right? Because the Boltzmann population will readjust itself according to the splitting pattern of the ground state. Now you will say, hey, you're shitting us, then because obviously you also have the energy difference, right? So the A term thing. That is absolutely true, but the population difference effect is very much larger than the energy splitting effect. That's why I've drawn these two things on top of each other, although of course they're shifting too. But the population energy difference is that what wins out here, and that gives rise to that temperature dependent absorption shaped signal. And now for the B term, that is that place where everybody who's teaching MCD goes over, yeah, you know, then it's because there is not really a very good picture on it. So there is a very complicated equation, and what that complicated equation is simply telling you is that the magnetic field, so the Zeeman term, it leads to a mixing of excited states with each other. And that mixing of excited state, that gives rise to the MCD B term signal. So organic chemists have always been very keen on using MCD spectroscopy in a way that, that, as I said, just place a magnet into the CD spectrometer and measure. And there's a very famous guy who has ever heard the name Carl Djerassi? Never? Okay, so so this guy has invented contraception, and before he did that and got very rich with that, he also was an MCD spectroscopist. And so I very vividly remember that there was an issue of JACS from, I think, the mid-70s or so, where he had like 14 or 15 back-to-back JACS papers, each 1 page long, and each just reporting the MCD B-term spectrum of one amino acid. And those were the days, where you could get away with that. But B-term MCD then is often used in organic chemistry or on non-magnetic compounds, and is basically strictly used in a fingerprinting way. I've never seen anyone doing a detailed analysis of a B-term MCD spectrum. So you can estimate the relative sizes of the A and B and C terms for our model P to S transitions under some reasonable assumption that you have a line width of about 1,000 nanometers and a transition energy of about 10,000 nanometers, and then KT is room temperature, it's about 200 wave numbers, and so you will find that here the ratio of A to B to C is about 1 to 0.125. Yeah? So already at room temperature, the C term is like 5 times more intense than an A term. Now cool that down to like 4 Kelvin and the C term is like 500 times more intense than the A term. That means when you do transition metal MCD, it's basically all C term. Yeah, so 99% of everything that you're looking at is actually C term. Okay. Yeah, and here is then a more in-depth view of what I've told you about the MCD saturation curve. So when you now look at the C term MCD and you ask yourself about the Boltzmann population in a spin 1/2 system, then you will find that this is a Boltzmann population of the M sub s minus 1/2 and M sub s plus 1/2. And when you can take this and calculate the population difference, and can make a Taylor expansion, for example, as a function of B over T or something, and you will relatively immediately derive the equation that this is proportional to the hyperbolic tangent that looks like this. And that is then how you can use MCD to measure the G value. Yeah. So at small magnetic fields, then the MCD is always linear with respect to the magnetic field, and then it eventually saturates off, and it saturates off when the population difference is at maximum. Yeah. Good. Now let's look a little bit into the origin of the MCD for high spin systems. And I've shown you already that they have these interesting nesting effects and that interesting wavelength dependent, and I've already hinted at that that has something to do with the polarization of these transitions. And so many years ago, I think when I was about your age, then I made a theory for that. And it's a bit complicated. I don't want to lead you through that, but like the principles of that treatment is looking at the mechanisms that give MCD intensity. And for that mechanism, you have to have spin-orbit coupling, right? For the EPR G-tensor shift, you also have to have spin-orbit coupling. And now you have the selection rules of the electric dipole operator and the selection rules of the spin-orbit coupling operator, right? And so here are the magnetic sublevels of the ground state, and here you have the magnetic sublevels of the excited state. And in terms of the electric dipole operator, your selection rule is delta M sub s equals 0, right? So in order to have a non-zero value, you have to have the same magnetic quantum number. But in terms of spin-orbit coupling, it can mix then any M sub s levels with m prime equals m or m plus minus 1. So there is that complicated relationship between them. And now you can work through all that stuff, and it's a very lengthy derivation, but you can derive then a very interesting equation, and that is then kind of the master equation for nonlinear MCD. Yeah? If you take the linear limit of those, you would recover Stevens' theory. But this one always works, and I think what that equation brings out is really the connection between EPR spectroscopy and optical spectroscopy. And it says that the MCD signal is proportional to a constant, and then there is a sum over the magnetic sublevels of the ground state, its Boltzmann population, and then for each of these magnetic sublevels you have spin expectation values. So that is the spin expectation values of the ith magnetic sublevel of the ground state in the x, y, and z direction. L is a transition cosine because you have to integrate that over all molecular orientations relative to the external magnetic field. And now these blue quantities, these are product of transition moments. I'll explain that in a second. But here you see then how the polarization of the transition is filtering, so to say, which part of the magnetism you see. Right? So if all of these are 1, then you basically get the squid signal, then it's in the MCD. Right? But for example, if you have something, let the easy axis of the magnetization be the z direction, then an xy polarized transition gives you then the part of the magnetism that is coming from the easy axis, and that is that very, very steep unnested behavior, whereas if that is 0 and either of these two is non-zero, then you get that off-axis magnetism and polarization. So it's quite nice. The fact of the matter is that you can use a standard spin Hamiltonian to calculate these Boltzmann populations and these spin expectation values, and that is really the crucial key step where you connect the world of the spin Hamiltonian with the world of the MCD spectroscopy. Yeah? So the excited state information is here in these polarization products, and the ground state or EPR kind of information is here in the Boltzmann populations and the spin expectation values. So that's very nice. And there was a first test of that theory back in the day where people had measured the MCD response of a high spin iron 3 porphyrin. And that has an S equals 5½ ground state with relatively large zero field splitting. And so you get 3 Kramer's doublets. And all of these 3 Kramer's doublets, they contribute to the MCD spectrum. And what that theory then allows you is to predict the weight with which each of these 3 Kramer's doublet contribute to the MCD spectrum as a function of 1 over the temperature. And so what you see here, I forgot then, is I think blue is the experiment and red is the prediction of the theory. And and you see that it's kind of pretty much spot on. So there is no fiddling, no fitting, no fudging, no nothing. That is just simply how it comes out of the theory compared to what people have fitted to the experiment. Yeah. So that's satisfying, and that I think is also now the theory that everybody who is doing MCD on transition metal complexes is using. Let me make a quick comment on MCD intensity. So throughout the development of that theory, you identify basically 3 mechanisms. So the first one is the direct transition of the electronic ground state and the electronic excited state. That gives a pretty much negligible contribution to the MCD intensity. And the other 2 mechanisms involve the interaction of either the ground state or the excited state with an intermediate state K here by spin-orbit coupling. And that gives very fundamentally different contributions to the MCD spectrum. Yeah? So here, in mechanism number 2, you have a spin-orbit coupling relationship between the ground state A and the excited state K while you observe then the transition from A to J. And here it's just the way around. You have a spin-orbit coupling between states K and J, and you observe the transition to A and J. And it turns out to be the case that you can show on paper and pencil that whatever MCD intensity state K is inducing on state J, it is a negative the way around, right? So when you have this mechanism, you always have, say, a positive peak going from A to J and a negative peak going from A to K. Yeah, so that was always giving these like pairs of, of plus and minus MCD transitions, and that is the signature of this mechanism. So that is a pseudo A type of situation where when K and J are close in energy and they have a spin orbit coupling, then you always get these pseudo A terms. Whereas no such rule exists for the spin orbit coupling of intermediate state K to the ground state, and something that is then dominated by spin orbit coupling with the ground state only has usually has MCD of just one sign. So that is something that comes out here. So for example, in this spectrum that is at copper side, you have this very intense pseudo-A term here that is coming from a set of transitions that is orthogonally polarized. One of them is X polarized and one of them is Y polarized. And by spin orbit coupling, you get then these XY, that this product, this effective transition moment product of MXY that is unequal 0. You can also predict the sign of the MCD. So if you're really serious about it, then you can like take the molecular orbital diagram that you've calculated, and once you start assigning these transitions, and there are some graphical rules that I don't have really time to go into it, but it is kind of a real fun game. So you draw yourself. You're saying no, it's not fun. I made Dan do it like a while ago, and I think it was very successful. But so essentially, like you're taking your orbitals and then you play like little rotation games with paper and pencil. And if you do it correctly, then you can successfully predict whether the MCD is supposed to be positive or negative. It's all phase relationships between these these orbitals. Yeah. This, for example, here is an MCD spectrum of a low-spin iron-3 compound, and low-spin iron-3 has very strong in-state spin-orbit coupling because that's a doublet T2G ground state, and that very ground state dominated by ground state spin-orbit coupling dominated MCD. That is basically everything is of one sign. That is characteristic. Yeah. Yeah, and that is probably the most important that I want to show you about MCD intensities. So you can now define, if you do that simultaneous fit, then for each band that you have an intensity in the absorption spectrum and you have an intensity on the MCD spectrum, and you can normalize the effect of temperature and magnetic field away, right? And that is then the intrinsic intensity of that band in the MCD, yeah? And so that is, and what you define then is the so-called C over D ratio. That is essentially then the ratio of the intensity of the MCD band divided by the intensity of the absorption band. And that prefactor here is basically taking the temperature and magnetic field dependence out of the MCD band. Yeah, so that is nothing else than the area under your fitted Gaussian in the MCD and the area of your fitted Gaussian under the absorption. And now there are at least empirical rules that can be justified relatively readily from theory, but like just empirically, you can see if there is the C over D ratio of larger than about 0.01. That's a signature of a DD transition, and a C over D ratio of smaller than about 0.01, that's a signature of a charge transfer transition, right? And so there is an experimental way of disentangling in an absorption spectrum what is a LMCT transition or an MLCT transition and a DD transition. And so once you get more serious about assigning stuff, that's really useful, right? Let me give you an example here. That is copper tetrachloride. It's one of in physical inorganic chemistry, that is kind of like the H2 molecule of physical inorganic chemistry. And you can see that here in the absorption, you have relatively weak absorption band, and relative to that you have relatively strong CD bands, whereas you have that very, very strong LMCT band here that comes then with a C over D ratio of 0.002, and that is then the signature of the charge transfer band. Yeah? And you can, of course, now dig deeper into to the DD region of that spectrum, and if you apply the rules correctly, you can from the pattern of positive and negative MCD bands, you can confidently assign these MCD spectra. So this pseudo A term here, that is then the dxzyz pair of transitions into dx squared minus y squared, and that leaves the dz squared to the SOMO transition here, and then the dxy to dx squared minus y squared there. So that is a way that, so only to, without going into too much detail, illustrating like how powerful MCD spectroscopy is when you really want to go into the details of the electronic structure, and then rather than believing your calculation in which order these bands have to come, you can actually really see it. And there are few places in the science that we have been doing where the assignment of the MCD spectrum also then gave key clues about the reactivity of these compounds by being able to deduce, experimentally deduce, the level scheme. I think we still have 5 minutes, but I think I don't want to rush you through another chapter of these notes, and instead we may have a little discussion. Yeah. So thank you very much for your attention. I hope that was not totally uninteresting. Yeah.